So today's lab experiment is on RC circuits. You'll be seeing how a resistor and a capacitor connected in series work, and that there is a measurable amount of time that it takes for the capacitor to either fully charge or fully discharge. And you can figure out a quantity called the time constant of an RC circuit. In theory, it's equal to the product of resistance times capacitance, but you can also measure that time constant as well, and that's what we're going to be doing in this particular experiment. So, just talk a little bit about what an RC circuit is first. It's a resistor and a capacitor connected in series. Once they are connected, the capacitor will gain charge, and it will gain charge until the voltage across the capacitor equals the voltage feeding into the RC circuit. Over the course of time that it's building up, or that the charge is building up, the voltage feeding in will equal the voltage across the capacitor plus the voltage across the resistor. And so the voltage across the resistor is proportional to the current, which is the rate of change of the amount of charge that builds up in the capacitor with respect to time. So the amount of charge moving through the current per time is also the amount of charge building up in the capacitor per time. And if they are connected in series with no power supply, the capacitor will discharge. So if there's no potential difference, but there is charge in the capacitor, eventually the electrons that accumulate on one side of the capacitor, the extra electrons, will move through the resistor to the other side of the capacitor. And at which point the capacitor's charge will dwindle down to zero. The process without a resistance, the process of charging or discharging the capacitor would take place instantaneously. But with a resistor, there takes a certain amount of time. And so to define that relationship, you need to define a time constant, which is equal to R times C, the product of resistance times capacitance. You've seen that in class, so I won't go through the full derivation here. But I'll talk about the results of the derivation. So the voltage across feeding into the circuit is equal to the voltage across the capacitor, which is Q over C, plus I over R, the voltage across the resistor. And again, I is equal to dQ over dt. So that's a differential equation, and when you solve for that equation, you get Q as a function of time for a charging capacitor is equal to the maximum Q. So the charge in the capacitor when it's the voltage across the capacitor is the same as the voltage feeding in. So the maximum Q times 1 minus e to the minus t over RC, or to the minus t over tau. The maximum charge is equal to C times the maximum voltage, which is the voltage feeding into that segment of the circuit. The discharging capacitor is simply a decreasing exponential function. So the maximum charge is whatever charge was on the capacitor when the discharging circuit was connected. And so Q is equal to Q max times e to the negative t over RC. In both cases, the current decreases exponentially. So it has its maximum value right at t equals 0, the moment the circuit is connected. And I is equal to I max times e to the negative t over RC. I max is equal to the maximum voltage divided by R. So the procedure has a couple of steps. The first step is we're going to be looking at a charging and discharging capacitor in real time. So we have a fairly large capacitor with the resistance. We set the power supply voltage to 2 volts. So we have, I didn't use 2 capacitors, I used the variable resistor to get 43,000 kiloohms. So every 15 seconds, we measure the voltage across the resistor and the voltage across the capacitor. So you'll see in the recording, we use 2 DMMs for that. We repeat the process for discharging. And so for both charging and discharging, and make sure you label which is which clearly, you're plotting the voltage across the capacitor versus time. Now, the voltage across the capacitor should be directly proportional to the charge across the capacitor. and find the half-life, or the time it takes to charge or discharge the capacitor halfway. So it should be the same value. You're going to be asked to derive equation 9 in your manual for this and calculate an experimental value for the time constant. For part 2, we're going to use a special kind of voltmeter called an oscilloscope that measures voltages over very, very small periods of time. So it's extremely time sensitive. We're going to use a much smaller capacitor for this part. And so we set it up so you're having a square wave. So half the time it's at your maximum voltage, and then half the time it's at 0. And so you're asked, how long does it take for the voltage to reach half the maximum value? And you'll be able to figure out that reading from the oscilloscope. And again, go through the process you went through in the first part of using that to figure a value of the time constant, compare it to the product of R times C. And so don't forget the 6 questions on page 58 as well. For the error analysis, when you're measuring the time constant from the half time, or the time it takes to charge halfway or discharge halfway, the uncertainty in tau is equal to the uncertainty in the half-time measurement divided by the log of 2. For the calculated value of tau, the uncertainty of tau is equal to that calculated value multiplied by the square root of the percent uncertainty, or the fractional uncertainty, in R squared plus the fractional uncertainty in C squared. And so your values of tau should agree with those uncertainties. If they don't, comment on why you think they don't. Okay, so if you have any further questions about the theory of the procedure, do not hesitate to email me. Otherwise, good luck. The lab report and the video are due on Monday.